Hello, I am Beryl Nyanaraj. This work titled To the Point From Dynamic Heatmap Videos to Gaze Points aims to find low-cost technology solutions for eye tracking, such as web cameras for online healthcare surveys conducted in low-middle income countries like India. Here we have used a web camera-based non-commercial software solution to record eye movements in the form of dynamic attention map videos. Here is a sample of one of the recorded dynamic attention map videos from a non-commercial eye gaze recording software. Notice the uncertainty around each hotspot. Each hotspot is formed by using the fixation count and fixation duration. By temporally ordering such heat map frames, one gets dynamic attention map videos. Now, our problem is to localize the gaze point as a two-dimensional x, y coordinate for each frame of the video. Gaze points are needed to apply statistical approaches to the recorded data. Having gaze points also allows one to compute fixation features and saccade features, which are then used to compute further metrics, as in the case of cognitive load. While image processing techniques have been used to solve the problem of hotspot detection in the past, we find that due to the poor quality of the recorded videos and changing frame backgrounds, the localization of hotspot is challenging and often fails. Hence, we propose to solve this problem by using an object detection method. Using deep neural networks, we pose the problem of hotspot detection as an object detection 1 and identify the latest changing hotspot for each frame. Once the bounding box of the hotspot is identified, we localize the area of change within the hotspot by comparing the hotspot to the one in the previous frame. Once the changed portion is identified, we choose the pixel with maximum intensity to represent the gaze point. We train the neural network models using annotated dynamic attention map videos to predict the rectangular bounding box around the latest changing hotspot in each frame of the video. Each frame has either 1 or 0 rectangular bounding boxes pertaining to the hotspot. Once the model is trained, it can predict bounding boxes around latest changing hotspot for each frame in a test video. A sample of the output is shown here. We compare the results obtained for 3 different neural networks, namely Detection Transformer, YOLO version 8, and Faster RCNN. We ran the training for 100 epochs and find that the best loss values were around 70 epochs. A test video was input to the 3 models for hotspot detection. The pink dot seen within each predicted bounding box is the estimated gaze point given as a two-dimensional x, y screen coordinate. Using metrics, we quantify the performance of the models and find that Detection Transformer performed better than the other 2 with a good classification accuracy and mean intersection over union value. This work serves as a proof of concept for our proposed novel method for determining the most probable gaze point from dynamic attention map videos. From our experimentation with 3 different neural network models, we find that the baseline detection transformer performed the best. We have annotated the training data set used for all the models' training, which is also released in our GitHub repository. Thank you for your attention. Please scan the QR code for more details.